Hello everyone, this is section 10.2 on matrix representation of graphs. So now let's talk about adjacency matrices and directed graphs. So let's be a directed graph with order of vertices b1, b2 up to bn. The adjacency matrix of G is going to be the n by n matrix Aij, where Aij is going to represent the number of arrows that are going from bi to bj. So in here, loops are going to contribute to the diagonal entries of AII of the matrix, and multiple arrows between the same pair will increase the count. Changing the order of the vertices is going to change the matrix. So let's take a look at that. So this is a directed graph here. Notice that it's called directed because we have direction of how the edges are moving in one direction or the other. So here we have this edge is going from b1 to b2, and this edge is going from b2 to b1. Now we have this edge going here from b1 to b3, two edges going from b2 to b3, and one edge going from b3 to itself. Now because we're counting arrows, so for example for b1, we're going to check how many arrows are going from b1 to bj. So from b1 to b1, nothing is really going in that direction. And from b1 to b2, you have that one arrow is going in that direction. And from b1 to b3, you have one arrow in that direction. So that's why we have 1 and 1 here. Now let's examine the node b2. From b2, you have that one arrow is going to b1. So we represent that by going with 1 here. We have 0 arrows from b2 to itself, so that's represented here. And now we have 2 arrows going from b2 towards b3. So you can see this arrow, so because of that we count and put 2 in here. Now from b3 there is no arrow going anywhere but to the same place. So it goes from b3 to b3, so we get this 1 in here. Notice that the rows are considered from from the node I, and we're always considering that we're going from the node bi, and the columns are representing the j, so pretty much all the arrows going into the node bj. So the entry A23 is equals 2, right? So it's row 2, column 3, means that we have 2 arrows going from the node 2 towards the node 3. A33 equals 1 means that there's a loop from B3 to itself. Now let's talk about adjacency matrices when we don't have direction on the graph. So far we've seen undirected graphs, which is the most common, where we have vertices b1 to bn. And so the adjacency matrix is a similar matrix where we have Aij, but Aij is now the number of edges that are connecting the node bi and bj. So here's not about arrows, but number of edges that are connecting. The loops of bi are only going to contribute 1 to the diagonal entries. Now notice the adjacency matrix of an undirected graph is always going to be symmetric. So that means that Aij is going to be the same as Aj. This is because an edge between bj and bi is counted the same way in both directions. So now let's see an example here. We have this graph. Notice that we have the following connections. b1 is connected to b2 towards one edge, b1, and so it's reflected here. It doesn't have connections to itself, so it's 0. With b3 is connected by 2 edges, this and this, and with b4, b1 is not connected, so we have a 0. Now the node b2 is connected to b1, is connected to b3, and is connected to b4, but is not connected to itself. So we're going to have 1 everywhere, but at the column 2. For b3, notice that this is connected by 2 edges with b1, so that's going to be reflected here. Is connected with 1 edge with b2, and is connected with 1 edge with b4, so you see that reflected in there. It's not connected to itself, so we got a 0 in there. And similar with before it's only connected to B2 and B3, so you see the ones in there. It's not connected to itself, it's not connected to B1, so we get zeros on those positions. Now, this matrix is going to be symmetric. The row sum is going to give you the vertex degrees, actually. So, for example, the degree of B1 is 0 plus 1 plus 2 plus 0, which is going to give you 3. And so notice that for the node B1, this is giving you the degrees, which is the number of edges that are coming out of B1. So you can use a row sum to find the degrees. The definition of matrix multiplication given by linear algebra is that if you have two matrices, one let's say from dimension n times k, and another matrix of dimension k times n, then the product matrix AB is going to be a new matrix C of n by n dimension, so that the entries of that matrix are going to be from the form Cij, where Cij can be seen as the sum of the multiplication of the entries of the row I of A times the column J of B. So as you can see here, we have AI1 B1J plus AI2 plus B2J, so on and so forth until we get to AIK times BKJ. One example of that would be, consider these two matrices. We have the matrix 2, 1, 0, 3, 1, 4, 2, 0. So we're going to multiply, we multiply row by column. So 2, 2, 1 is going to be multiplied with 1, 2, and that's going to be the first entry. So 2 times 1 plus 1 times 2. And so that's my first entry. Now, the second entry of the column is going to be 1 times 0 plus 2 times 3. And so that's my entry here. And now for the second column, we have 4 times 2 plus 1 times 0, 4 times 0 plus 0 times 3. Once that we have that, we solve what these values are, and this is going to be my new matrix multiplication. In general, remember, the matrix multiplication of A times B is not going to be the same that B times A. Now, obviously, we are interested in matrix multiplication when we're talking about graph, because we're going to be producing the multiplication of certain matrices, and then that's going to help us tell different things. So, for example, we're going to be able to count walks via matrix powers. How's that? Well, if you consider a graph with n vertices and their adjacency matrix for that particular graph, then for any positive integer n, if you have the a power to the n matrix, that is going to give me the number of walk of length n from bi to bj. Why? Well, because each entry of, let's say, a squared, which is a times a, is going to sum products of the form aik times akj, which is going to count the number of ways that you go from the node bj to some intermediate node bk and then to bj. Here, exactly the length of two walks, or the length two walks, really. So how many two walks length or walks of length 2 am I going to have to go from I to j? The practical use of this is that without listing those specific walks, you can determine the connectivity and the reachability of the matrix just by computing the power. Okay? Connectivity is, of course, remember how connected is the graph, and reachability is the ability of one node to reach others. That's especially useful for algorithms that work over trees, and algorithms that work like that, like depth first search, and others. Now, let's do an example of walk counting. So we have this graph B1, B2, B3, and that's going to be given by this adjacency matrix. Notice that every node is connected to the other two, but not connected to itself. So we have A1 is going to be this matrix with, remember, zeros in the diagonal. But now when we do a square, notice that we're going to get a11 being 2, a22 being 2, and a12 being 1, and 833 being 2 again. Now, a square of 1, 1 equals 2 means that there's 2 length walks from B1 to B1. And yeah, that makes sense. So I can go from B1 to B2 and then back to B1. Or I can do B1, B3, and then come back to B1. Okay, those are 2 lengths walks. So I go from here to here and then backwards. I go from here to here and then backwards. Now, when I say a square of 1, 2 is equals 1, it means that there's 1 length 2 walks from B1 to B2. And that, of course, is going to be, I take from B1, then go to B3, and then go to B2. Now let's talk about connected components via the block structure in the matrix. So the theorem is, if G is a graph that has connected components, G1, G2 up to Gk, and we order the vertices by components, then the adjacency matrix is going to be a block diagonal. So that will mean that we're going to have a matrix here of adjacency that is going to have blocks per each of the connected components. Now, the interpretation of this is that the off-diagonal 0 blocks means that there's no edge crossing between the components. This gives a visual way to detect disconnected graph directly from the adjacency matrix. Now, the notion of graph isomorphism is something that we can consider when we're comparing 2 graphs. So 2 graphs, G and G prime, are going to be isomorphic if there is a one-to-one onto functions from the vertices of the graph of G to the vertices of the graph of G prime, and from the edges of G to the edges of G prime, such that the vertex B is an endpoint of an edge E, if and only if G of B is an endpoint of H of E on G. So the intuition of this is that 2 graphs are isomorphic if you can kind of draw them or draw the sum graph in 2 different ways. So for example, here we have the graph ABC being the graph G, and then we have the graph G prime with the node CXY. As you can be, like, kind of the shape is the same, even if the name of the vertex is different, but we can kind of identify, let's say, A with C, B with X, and C with Y. And so that relationship, that way of identifying this, that they have the same shape, the same type of connection, the same nodes, is the way that we can say that they're isomorphic. Now, an isomorphic invariant is a property that is going to be preserved by any isomorphism. So if G and G prime differ in any of the invariants, they're not going to be isomorphic. This is pretty much one of the ways that you can check very quickly if 2 graphs are or not isomorphic. So the useful invariance that you can check is that they have the same number of vertices, that they have the same number of edges, that they have the same degree sequence. So they have a sorted list of all the vertex degrees and they match. Also, they have to have the same number of connected components and the same number of circuit of each length. One example of this would be something like this. So G has the degree sequence 1, 2, 3, 4, and G prime has this degree sequence 1, 2, 2, 3. This is not going to be isomorphic as the sequence of degree differ. Regardless of how the edges are drawn, because the degree sequence is not the same, then they're not going to be isomorphic. Now, once that we have graph, with certain conditions, we can have that the graph create a spanning trees. So in a spanning tree of a graph is a small subgraph of G that contains every original vertex of G, but it's going to be a tree. So it's connected and it's circuit free. As a proposition, we can say that every connected graph is going to have a spanning tree, and any two spanning tree for the same graph has the same number of edges. Why is this useful? Well, the spanning tree is one of the ways that is most economical way to have a connected subgraph. It connects all the vertices using all the possible few edges. So you can imagine if you're trying to use a network to create a way to cover multiple places, then you get a spanning tree of that particular graph, and that will be one of the ways that you will be covering the entire entire network without having to spend multiple travels among the different nodes. So let's see an example of a spanning tree. Here we have the graph G. And so notice that this is a graph that it has a circuit pretty much, but we can break it apart. So it's only going to be a tree. So if we remove the edges BC and the edges CD, then we have a spanning tree. It covers every single one of the nodes and is a tree. It doesn't end up being a circuit. Here we have 4 vertices and 3 edges, and it's not. We have no circuits and it's connected. Now you can have multiple spanning tree SS. You can pretty much do the same if you do ACDB, but instead of removing CD, you can remove, I don't know, AB and BC. That's something that you can do. So not necessarily you're going to have a single spanning tree. Okay, so in summary, in this section, we define the notion of adjacency matrix. We also mentioned that with matrix multiplication, in particular from the adjacency matrices, we can count the number of walks of length n that we have from a particular node to another. The block structure is something that we can observe. If a graph is disconnected, then the adjacency matrix is going to be ordered by component and block diagonals. And we have the spanning trees, which are subgraphs that contains all vertices and that are trees and that connected and circuit free. Getting every in every connected graph is going to have a spanning tree. Now, be very careful not to assume that matrix multiplication is commutative. When you're using the wall counting theorem, you got to remember that a to the n is a multiply n times, not the sum. Don't forget that the order of vertices matter. A different order gives a different but equivalent matrices. So just make sure that you're always labeling rows and columns clearly with the vertex names. Make sure that when you're handling loop and undirected graph, you're paying attention to the contribution. A loop of BI that contributes 1 to II, not 2. And loops also contributes 2 to the degree of BI. In this case, it will be counted twice in degree, but once in the matrix entry. Now, be very careful not to confuse the matrix with the power. 8 is counting edges, let one walks that we have, and 8 power to the n is going to count length in walks. All right. Okay. So in the next section, we're going to see trees and rooted trees.